Dear students, today we start the unit 3rd of our syllabus, and the first topic of the unit 3rd is what we call normal section of a surface at a point. Now first the definition is given in your notes, so let's start with what do we mean by the word section. So you have a surface, any surface. For simplicity's sake, let us take a plane and we intersect it with another plane. So they will intersect in a curve. Oh, I have not drawn it well. Okay, let me delete it. So what I was saying, so I have a plane and then you intersect it with another plane. So what do you get? So you get a line of intersection, planes where these two things intersect. Similarly, you could have a sphere. So you have a sphere and you intersect it with a plane. So you get a curve that is common to both, that is the intersection, the common to both the surface and the plane. They call it section of the surface by this plane, section of this plane by another plane. Similarly, if you had a cylinder and if you let this be the cylinder and you intersected it with a plane perpendicular to the generator, then you would get a circle. This circle is the curve of intersection of this plane and the cylinder. So this is a section of the cylinder. So this curve is a section of the cylinder. Similarly, I could have a general surface and then I intersect it with a plane. So I would get a curve of intersection of this surface. Now this would be the section of the surface by this plane. Now what is a normal section? Now normal section is the section of a surface by a special plane. So I have a surface, a general surface now which I usually draw like this. I have a point P here and I know there is also at each point for a regular surface I can think of the surface normal, the surface unit normal. N, which is basically R sub u cross R sub v divided by its length, which is a unit vector at each point of a regular surface. Now, if I have a plane which contains this surface normal, so so it intersects the surface along a curve, and we call that curve the normal section of that surface at this point P, where I have drawn the surface normal. In this way, I could also take the same plane and change its direction a bit, which still contains the surface normal, and I will get another curve of intersection. So at this point P, there is infinitely many normal sections that I get. Normal section means the curve of intersection of the surface and the plane which contains the surface unit normal at that point. So at each point on the regular surface, there are infinitely many which I can get by rotating this plane, the plane which contains the surface normal. So that was the definition. Or should I write the definition? Okay, let me see. Okay, so let me write down the definition. A plane okay, a plane, see, let me write down the curve of intersection of the plane containing the surface unit normal n at P a point on the surface. P is a point on the surface. On the surface, what have I written? The curve of intersection of the plane containing the surface normal at P and the surface. ये जो curve है, it's called normal section at P. Is the normal section at P. Now, if I take any other plane which cuts the surface, but it does not contain the surface normal, we call that oblique section. Any section, any curve of intersection of a plane which does not contain the surface normal, we call that curve oblique section. Oblique section means any section which is not normal section. By section, we mean the curve of intersection of a plane and the surface. And if that plane contains the normal, that is the normal section. Okay, now if I have a surface, I usually draw it like that, but it could be in any orientation. You have a surface, could be like this. So I usually draw it like this because it's easier to draw the tangent plane and other stuff related to the surface. Now what I'm trying to say, now when I have a normal section, so normal section is essentially a curve. Now this curve has at each point a tangent and principal normal, a binormal, depending upon the orientation of the curve. So of course this lies inside the tangent plane, the plane which contains the surface normal, this normal section. So I've got this principal normal must lie inside that plane. And if it is a normal section, then n must be parallel to n. Now we make a convention. Now both of them are vectors of magnitude 1 and they are parallel. So that means n can be either plus n or minus n. But we choose our orientation in such a way, that means we say if you have a curve of normal section, right? And if n is like this, the surface normal, you have a normal section like this and n is like this, we say here the curvature is positive. And if the situation is reversed, normal is in this direction and curve is curved downwards, we say it has negative curvature. It is just a convention. So by this choice, then n is equal to n, where n is the principal normal of the normal section. And of course this capital N is the unit surface norm at a point, of course. Okay, once I have decided that, then the next thing we do is to find the curvature of the normal section, in terms of first and second order fundamental magnitudes. First and second order fundamental magnitudes. By that I mean, what are the first and second order fundamental magnitudes? They are E, F, G and LMN. I can find the curvature of this curve, curvature of the normal section in terms of the first and second order fundamental magnitudes. For that, we say let K sub n denote the curvature of the normal section. Curvature of the normal section. If that is the case, then we know that and let me write it down. We know that T dash is equal to k times n. In this case, since I have, this is the Serif-Renyi equation, one of the Serif-Renyi equations, and since I had noted the curvature of this normal section by k sub n, right, t dash is nothing but t is unit tangent vector, so this is basically r double dash. So r double dash is equal to kn sub n, but since by my choice of this curvature, what I call positive curvature and negative curvature, once I do that, that means I can write it as, k sub n, this capital N. So r double dash is t dash, which is k sub n, because k sub n is the curvature of this curve called normal section. So that means if I take the dot product with n on both sides, obvious, if you just have to take the dot product, that k sub n is equal to r double dash dot n. Okay, because n dot n is 1. So this is my curvature. Now remember that this curve lies on the plane which contains n, but it also lies on the surface. So I have a curve which I have taken to be given by arc length. I have dash means differentiation with respect to arc length. It is a situation like this, right? And of course r double dash ka matlab hai, it is the second derivative of this r with respect to s, right? But since this curve also lies on the surface, it should be a composition of this type. It should be r is equal to r at u at s and v at s. And using the chain rule, r is equal to dr by ds. By chain rule, this should be equal to del r by del u into du by ds plus del r by del v into dv by dv by ds. So this is just the chain rule. So which is r sub u into u dash in, as per our notation, r sub v into v dash, which is the derivative with respect dash ka matlab derivative with respect to s. And but since I want triple curvature, means that I want the second derivative of, I want r double dash. So differentiate it again with respect to s, and the rules of differentiation, I should get r